So a while back, we went through a theoretical ball toss upward to look at what happened to the ball's velocity and acceleration as it was moving up and down. And as you recall, we broke this ball toss into 5 different phases. As we were tossing the ball upward, then as it went upward after it left our hands, hit the apogee, came back down, and then slows down as it hits the earth and digs itself into the earth. So the question is, how can we actually see if the free fall portion of that is constant acceleration or not? That's our goal here. And you're going to do a lab activity that does that. But for this case, we actually made some predictions after we learned a little bit about constant acceleration. We started just by tossing the ball up in the air a few times to get an idea of how much roughly the time it took for each one of the phases. And then we actually filled in what we knew about our height, position, or velocity for each one of the phases. And then we actually used our knowledge of what constant acceleration means to fill in the gaps in between our knowns. And we came up with this prediction for our process. And of course, along the way, we did have to make a couple of simplifying assumptions. We assumed while it was in the air, out of our hand, it was in free fall. We get a nice parabola, a linear function for the velocity, and a horizontal constant function for our acceleration. And we assumed that on the way up, even though we didn't know exactly what was going to happen, we made a rough estimate that it was going to be constant acceleration, even though we really think it's going to probably start low, go high, then go low for our acceleration, and something similar for when it hits the ground. So this was our rough estimate before we collected any data. And the question is, what happens after we collect our data? Can we actually go back and show that our theory was correct? And this is essentially what you have to do for your lab. We've got a theory of what should happen, and then you're going to go through, collect data, and analyze that data and show that that happened or not. So here's the Logger Pro data we collected for this exercise. Just an overview of Logger Pro. Basically, the sensor is plugged into the USB port into this. We were using the sonar sensor. And as soon as I plugged it in, it automatically set up a position and a velocity graph for us to use. Under the data collection key, I actually extended the duration of the timing of the sonar probe to go for 20 seconds to allow me to throw it multiple times up in the air until I can get a good toss. You can also adjust the sampling rate, how many samples per second you want. And I used their standard values that they had suggested. I actually ran the experiment, and I tossed it several times. And it looks like I have one good set of data right here. And so I'd like to focus on that set of data, ignore all the other data. The other thing I would like is I've only got position and velocity graphs in here. I would also like to get an acceleration graph in here. Well, first, let's get rid of the excess data so it's not in our way and ignoring us. So I'm just going to lassoing the data I do not want. I'm just using my left mouse button to click and hold and drag. So all this data is sort of extraneous, and so I'm going to go under Experiment, actually under Edit. I'm going to strike through those data cells, and it'll blank those out so I don't need to look at those. And the same thing for all this other data at the end of the data set. I'll go under Edit, I'll strike through those cells. And so now all I really care about is this section of the graph. Now what I can do as well here, I would really like to stretch this graph out to take a look at it a little bit better. I can actually do that by running my cursor over the axis, and you'll see it changes its shape. Here you can see it changes to a flat line with an arrow off to the right, means I can stretch it off to the right. And I can do the same thing on the left side to stretch this out if I'd like to see the portions that I'd like to see. If you'd like to do it a little bit more direct route, I can actually right-click on the graph, hit Graph Options, and under my axes options, I'm really modifying the time axis, the quote-unquote x-axis, right? The horizontal axis is actually a time axis. And you'll notice I can also change what I would like. If I wanted to plot something else, I could change it right here as well. But what I'd like to do, rather than auto scaling, I'm going to switch to a manual scale. And I think the times I want to do is from around 2 seconds over to a little past 4 seconds. So maybe I'll go 2 seconds over to maybe 4.2 seconds. And as you can see, these two graphs are linked together, so it moved those spread those out together. I can do the same thing for the heights of these graphs. You can either manually adjust those by dragging them like so. Just click on your axis and shift things around, which, by the way, I've already done. They don't show up this way. You get a little bit of noise in there, and it'll be a little bit funky. So I can stretch things out like so, stretch out my scale. Or I can, once again, I'm going to right-click on the velocity graph, for example, hit Graph Options, and the time scale I've already adjusted for both of these. So now I can adjust my heights. It looks like the maximum value is less than 10 in both directions. And so I'm going to go ahead and hit Manual Scale, and I'm going to pick my top to be maybe 7 meters per second, and my bottom to be maybe -7 meters per second, and see if that fits. Let's just hit that and see if that all fits. That all fits perfectly. All right, so that's my position velocity. How do I get an acceleration graph in here? Well, what I can do is I can go up here and I can insert. You can pick an additional graph. Or actually, I'm going to hit the graph here. And it automatically presumes that I wanted acceleration. It's very presumptive. And what I can do is I can just resize this graph to match the sizes of the others. And this is nice. It actually, when I did it in this order, it also matched my time scales. So if you follow this order, it makes it easy on yourself. And then I'm just clicking on these to adjust the heights of these. And so I've got to squeeze things a little bit so I can see things, but well, you do the best you can. I'll cover up the time label because all the times are the same on these. In fact, I can just stretch it out like this so you can see a little bit taller graphs. So I'll just use my time axis on the bottom for all of these. All right. So there's my 3 graphs: position, velocity, acceleration. I guess the first thing is, well, is this what we expected? Let's take a look. Here's our original prediction. We curved up, had a parabola shape, downward facing parabola, and we curved back up again for the position. Velocity, we went up. We assumed it was a straight line. We know this probably is not exactly straight, but for a constant acceleration. But in the middle, for parts B, C, and D, we expected a linear function, and the slope of that function should be our gravitational acceleration constant. And then we had a very steep up right here if we were to run into a clay to stop us quickly. And then down below, especially for the portion where up in the air, we'd have constant acceleration, a horizontal function, a constant function. And for the most part, you can see those shapes occurring here. We have constant acceleration in this range. And if you look at the value, it's right around -10. That's what we'd expected it to be. If you'd like to look at the actual values, you can actually, probably the best way to do it, I actually have the examine tool up here. And if I click on the examine tool, I can actually click on any point along here. And you can see in this window, it's showing me all the different values. So it looks like it's bouncing around. I've got -10, -9.9, -9.8, 97, 93, 90. So it's giving me some different values as it runs through here. And the other way is just look at your graph. It looks like we're around 10 where we'd expect. So on this one, it's probably best just to look at the overall values of either on the graph, on the chart over here. By the way, our acceleration column is hidden. If I scroll over, here's our acceleration column. And you can see which items I've highlighted. And you can perhaps average those values out to see what average value you're getting for your acceleration. On our velocity versus time graph, what do we see here? Well, we had expected, and from here to here, it looks like we've got some sort of linear function, and that's what we expected. We expected once we release the ball, we should have some sort of linear function going on. And so from here to here, what we could do is try to use, and once again, if you look at our tools up above, I've got this is the examine tool to look at particular values. I've got a tangent tool here. Let me show you what the tangent tool does. This is my magical slope tool. And here's my magical slope, anywhere I'd like to see. And it gives me the values. All right, so you've got the magical slope tool. We're going to skip the statistics tool. But here I've got an integral tool, which takes the area. We'll use that in a second. Here's a linear fit tool, and this is what I'd like to use right now to see if I can fit a linear function to this and see what the slope is. And then we have a curve fit, which we can use perhaps on this upper graph. So using this highlighted data, I'll hit this tool here, and you notice it says R equal. That's a regression tool. And it's actually just fit a line straight through this data. And if you notice, this line, I'm not sure why it's doing this twice for me here. Oh, it's actually, it gives me a line, it's giving me a line of best fit for some reason for all three functions. I didn't really want that. So I just deleted those. And so here's my line of best fit for this linear function right here. And you'll notice that my line of best fit, there's my slope. It's negative 9.616 meters per second, meters per second squared. And of course, the actual value I was expecting to see was 9.80 meters per second squared. So we're pretty much in the right ballpark there for this experimental data. It's just very close to our negative 9.80. You could run a percent error on that, and you could explain what this graph means with your data, copy your data down to your graph, or print this out, and that would be your lab evidence that you could use with some explanations alongside it. So there's a line of best fit tool to actually see what the best fit on this line is. Let's check out up above. Well, before we do that, let's actually let me show you how to use the area tool. So one thing you could ask yourself, if we take the area that we've traveled from this point to this point, what are we actually looking at when we calculate this entire area? Well, that's our displacement. So that's our displacement as the ball is moving up from the person who is starting at, it looks like at about 0.5, 4, 3, 2. So they're actually about, if you look over in the column over here, you can see it as well in our data table to the left. So they're starting it out about a quarter of a meter high. So we're at 0.23, 0.24 meters above the ground. From the time we start actually moving it upward with our hands and then let go of it somewhere up at this peak, and the time it reaches its apogee, if we calculate the total area into this curve, we should be able to figure out how high it flew above from the point we started. And so let's actually try and see if this works. And so I've highlighted, once again, all I'm doing is clicking and holding and dragging across the area I would like to capture. I'm trying to capture this area. And then what I'm going to do is use this tool right here. It's called the integral tool. And in calculus, an integral is used to calculate areas under a curve. And so I'm going to click on that. And there's the integral for my function from over this value here where we're moving upward. And it gave us, it's 1.832 seconds times meters per second. Of course, the seconds cancel, and you have 1.832 meters. That's your displacement from the time we started moving up at around this time frame. Actually, you can see in this gray highlighted time frame. So let's remember, we're at 0.231 meters here, and apparently we've moved up when we got to our final time up here, a total of 1.832 meters. So if we add 1.832 to this number here, what's 1.832 plus 2.234? Well, that's 2.066. So if we actually take that number, look down at the bottom, the actual data shows us 2.072 versus a 2.066. And so you can see this integral gets us a very close value for this displacement that happened here. So we can take areas quite easily and then use that data, whatever way would help you explain your data. If we go up to the top curve, of course, really what we're interested in up above here is in the spot in the time frame that we're in constant acceleration, which should be on the portion of this graph where we actually are the linear portion. So I'm going to sort of select the portion that goes maybe from about here to here. That section from here to here where we're in free fall, that should be a perfect parabola. And so what we can do to check this is we can actually run a curve fit regression to see if we can fit a curve to this. And so this is the tool right here, our curve fit tool. And if I click on that, we get a whole menu of options here. So here's the data it sees that we've selected. Here's our curve, and here's the data we're trying to fit it to. And we can actually choose from a wide variety of functions to try to fit it. And of course, you could guess at what type of function this is, and you can see we have probably 20 different things to choose from. Or you could look at the theory behind this and predict what function it should be and use that. And of course, for constant acceleration, we did make a prediction. If we have constant acceleration, a horizontal acceleration versus time graph, that leads to a linear velocity versus time graph, which leads to a parabolic position versus time. So we should be a quadratic function, so we can check that one off. And then it asks, is there a time offset? Yeah, I'm not actually starting at 0, and I'd like to, in essence, make this look like it's the time axis passing through here. So I can actually include a time offset in here, and it'll actually start it at this first point I selected. And so you can see it inserts a time shift in my function here, t minus t naught, with my t naught being 2.604 seconds. And then what I can do, it'll automatically do a fit for us, and I can go ahead and hit try fit. In black, it's drawn the regression, the curve fit function I've tried to fit to our data, and in red, I have the actual data. And over here, it's just listing, here's our general form for a parabola ax squared plus bx plus c. Of course, we're using time. And it's telling us for our fit for this particular data, it's predicting that our a, b, and c are negative 4.810, 4.095, and 1.204. And your job is to interpret what each one of these coefficients means, and then explain how that supports your theory or not for your laboratory experiment. We would expect this to follow the form y equals 1/2 ay t squared plus vy naught times t plus y naught. That's what our theory says it should be. Now they told us that the equation they're giving us, which is down over here, they have y equals at squared plus bt plus c. All right, and what they're doing is they're basically saying, all right, for their A, B, and C, they should match our items up here, our coefficients. So our A should equal 1/2 AY. All right. And so for the A value, if you look down here, I've got our A value is negative 4.810 equals 1/2 AY. Therefore, if we multiply by 2 on both sides, we get what's 2 times negative 4.810, it's negative 9.620 meters per second squared equals AY. And of course, our goal was to show that this was a constant acceleration and that the value of the acceleration was 9.80 meters per second squared. And so you can compare these two values, and of course this is going downward, so we could add our sign in there if we'd like to. Remember, g is a magnitude only, but we can put negative g showing that it's a downward direction. We can add the direction using a sign. And so you can do a percent error to show how close these two numbers are. These are pretty close. This is pretty good data. All right, so it looks like this is showing us our acceleration is negative 9.620 meters per second squared. And the question is this a good fit for our data? How good is our fit? Well, the fit actually is going to be shown by how well your data actually passes through your curve, and I'm going to hit OK on this in a second. You'll see how well it fits. But if you look at this value down here called the RMSE, that's called the root mean square error. Root mean square error. And if you've done a regression analysis before, you might have heard of R squared correlation coefficient. If an R squared equals 1.00, you have a perfect fit. Your data and your graph are exactly on top of each other. R squareds of above 90% or so are pretty close fits. Below that, they're not so good. This is just another way of doing that error, and I'm going to show you in a second what that means. So let me go ahead and click OK on this, and you'll see when I clicked OK, it actually drew in black here. You can see, and remember, I only fit from here to here, and so you can see how my black and red lines are fitting next to each other over here, and they're fairly well on top of each other. And this value here tells us how far we're off on average. So, and you can see there's a slight difference between, if you look closely here. Here, our black line is a bit higher than the red line. In the middle, it's dead center in this area. It's a bit high over here. It's a bit low over here. So we're getting some variations along the way. But what this is doing, this number here shows us the average variation in the y value, or position value, of this graph. And it looks like for this graph, if we look, this is in meters, we're about 4.4 millimeters off on average for our actual height of the ball that we actually measured using sonar, as compared to the regression curve, this black regression curve model that we fit to it. So that's 4.4 millimeters. Well, is that a lot or a little? Well, you got to remember, we're running this over a height of, if you look, we start at about 1 meter up. We go from 1 meter up to 2 meters and back down to about 1 meter for our curve fit. And so this is over a 1 to 2 meter range we're doing this. So 4.4 millimeters out of 1 to 2 meters is a pretty small error, I would say. So we're pretty close fit. So it looks like then this appears to be a parabolic function. Of course, what does that mean? In terms of constant acceleration, you should be able to explain why a parabolic function is what we were looking for here. And here's our evidence that we do actually have a parabolic function for the portion of the curve where we're up in the air. So that's an example of how we can use LoggerPro to collect some data and then to analyze it. And of course, can you do this in a meaningful manner and a logical, organized manner for your lab activity is what you'll need to do. So what I would like you to do is just to play with this. You should download this software, and I'll provide a link that'll give you information on how to download the software. I'll provide this data set for you, and you play with this data set to see if you can come up with the same results.